Oh, welcome back. We will today look at high-performance computing. In particular, we'll look at how you solve systems of linear equations with computers. Doing this kind of matrix manipulations on the computer is very good for a number of reasons, particularly because computers are very good at this and humans are not terribly good at this. And much of what we now call high-performance computing, so that's a jargon word, involves dealing with matrices, because many scientific problems involve dealing with matrices. So this is an important topic. It's a little bit different. It's mainly dealing with mathematics, but as we'll see, we've already encountered some problems that we need high-performance computing with matrices, and this is the solution to do it. So let us look. Recall one such problem, our two weights hanging by strings. So this is a problem we talked about when we did searching. We talked about this a number of times. And here we have two weights, W1 and W2, angles, theta 1, theta 2 here, and theta 3 of the strings. And your problem is to discover what angles are and determine what the tensions in the string is. That's not so hard. The problem is, of course, you have to solve this as a simultaneous equation, and there's too many unknowns to do by hand. So we showed previously that there are actually 9 different unknowns in this problem, including the angles and the sines and the thetas of the angles and the 3 tensions. And we then could set the problem up as a matrix problem to solve after we say what the equations are. So the physics, which we discussed already, of statics gives us 9 equations to solve in 9 unknowns, and these are, as you see here, x1 times x7, x8 times x2, x1 squared. These are nonlinear equations. So we can't use linear algebra. We have to do something else. And what we discovered is that we could use our search techniques to solve this problem, and we have a solution. We've seen that already. And the solution is given here on equation 1 of slide 3. So take a look. It's familiar, I hope. If not, I'll tell you a little bit about it. Remember, here we have a matrix, a big matrix with derivatives, and we know every element in that matrix. Because we know the f's, those are just the equations we have to solve, and these are just the derivatives. And you can do those derivatives by hand, or you can let the computer do it, which is what we suggested. The unknowns here, with the question mark, are how much the x values differ from a first guess, which, us being clever types, we could figure out a fairly good guess. And then the right-hand side on this equation, indicating with a little 0 here, is a guess value. And we know what our first guess is. We make it up. So this is just the equations, the f's, evaluated the first guess. So what we need to solve for in equation 1 are these unknowns, delta x. Easy enough. This is now the standard form for linear equations. Okay, because now it's a linear equation. We've linearized it with this Newton-Raphson search method. So that A, which is the usual notation, is this matrix, n by n, here 9 by 9 matrix, x with a little vector symbol up here. Okay, that vector indicates that this is a column vector we're talking about. Usually in books, and in our book, that would be indicated with bold font, but bold on the screen here doesn't show up well. And the b is just the right-hand side of this equation, which is minus f, where f are just the equations. So this now is equation 2, a matrix problem we need to solve. Okay? Well, this is a good example. Many physical systems have matrix problems because many physical systems deal with simultaneous equations. And the reason we write them down as matrix equations is to make things look simpler, to make what appears like many different equations appear as one. So this is a more abstract way of doing things, but it makes it easier for us. If you know the mathematics, it makes everything much easier. When we deal with realistic problems, we deal with big systems, and then we deal with larger matrices. It doesn't really matter once you're learning how to compute what the size of the matrix is. When the matrix just gets larger, it means it takes the computer a lot longer. Computer has to sweat a lot more to get the answer, but you don't have to. So we can deal with small matrices now, but then when you go get jobs and you work for the big laboratories and big companies, you can deal with really big matrices. Okay. This is one of the areas where the computer is just an excellent tool for this. And you know why? Because if you're dealing with matrix multiplications like we have here, the same step is repeated time and again and again. That's terribly boring for humans to do by hand, but that's just what the computer excels at. They do the same thing over and over again. So here's the good news. So let's look now at slide 4. What's the good news? Well, the good news is that there are scientific subroutine libraries available for you to use, and they're by and large free, and all the hard work of solving these equations are there, and we recommend their use. So these are industrial strength. In other words, they're more than just homeworks. This is what you'd use to solve real problems, and many of them contain matrix subroutines or linear algebra packages, and that's what we're talking about. In my experience, these subroutine packages are at least 10 times faster, often 30 or 100 times faster than what you'd write your own if you just took a textbook, opened it up, and entered in the algorithm or the equation is given. Okay? Furthermore, they minimize round-off error. In other words, they're written just for computers, and so they know what to do to give good answers, and they minimize failure. They actually work, they'll give good answers. Okay. These routines are often robust, and that means that they work under a variety of situations, not just in the few trial cases you'll find in a homework problem. So your chance of success improves greatly, and they're generally flexible enough so that you can learn how to use one routine and use it in many different problems. Okay. Here is now the exception. You know, most everything we've done in this course and the preceding one and the ones to follow says you shouldn't look at algorithms as black boxes. We want you to look inside that black box here, okay, and, you know, see what the algorithm is, see how the problem is solved, and see what goes on. Now, for subroutine libraries to matrix problems, we recommend you don't write your own because they're not robust enough. You can certainly look at these routines, look inside, see how they're done, but do use them. Okay. One advantage for that, as we'll see, one reason is you can then use the same routine from the same library on your desktop, your laptop, go to supercomputer centers, often where they'll have a cluster of hundreds or hundreds of thousands of these computers, and the same routine has been rewritten to run on different processes. So that's very good. Okay, so that's really good. What's the cost? Well, nothing comes free. Okay. The first cost is that most of these libraries are not installed on the computers as you buy them. You have to get them from someplace else, install them, get all the pieces to run. That's not always trivial. The second cost is it's not obvious what routine you need to do any one thing. You have to look it up. The answer depends on the kind of arithmetic you're doing, integers, single, double, complex arithmetic, and then you have to pick out all the little subroutines that the one you care about uses. Because these methods are very powerful, but in part they're very modular. There's basic routines to do just the basic linear algebra pieces, and they're called by higher level routines, which are in turn called by higher and higher level. So the whole hierarchy of routines, and you need to know that. Finally, which something you don't want to hear, is that many of the routines were originally written in Fortran. And there's not that many Fortran programmers out there, although most large-scale, high-performance scientific computing is still done in Fortran. Now, many of them have been rewritten in C. A few, and we'll use them in this class, a few have been rewritten to Java as well, but many more are in C and Fortran. But if you know Java, you can run C, and if you're doing high-performance computing, if you're dealing with large matrices, you probably want to use C or Fortran, because as we have seen, or maybe you haven't, but then you will see, C and Fortran are much better at handling matrix large memory use than is Java. So let's look now at slide number 5, where we talk about different classes of matrix problems. So it's mainly mathematics, but these are important words to know because, why? Well, because you have to communicate, and also because you need to look up various classes of problems in these subroutine libraries. You have to know what they're called. They don't tell you for your problem particular, they have some very general names. So let's look at a few. First thing to remember is the rules of mathematics still apply. Even though the computer might be powerful, even though the matrices might get big, and even though these subroutine libraries are very smart, you can't violate mathematics. So for example, number 2, if you have more unknowns in an equation than you have equations, you cannot obtain a unique answer. Now these libraries are often so smart that they'll map out possible spaces that could be solutions. So just because the computer comes back with something, that doesn't mean it's the answer you want. It may mean you have a mistake you haven't thought about, and you have to understand the math. Likewise, if the equations are not linearly independent, in other words, 2 equations are really the same as one, or 3 of them are just some linear combination of another 2, then you don't have as many equations as you think you do. And again, the mathematics is not right, and the solution may come back, but it may be a non-unique solution. So you need to have exactly the same number of equations as unknowns, and every equation linearly independent if you want a unique solution. Sometimes you can have more equations than there are unknowns. This might be, some problem as you specified, and then a unique solution doesn't exist, but it's like fitting. You can get a best fit solution to those equations given what you know. Okay, so it's like what you know are data, you fit it as well as you can, and we'll talk more about data fitting in a lecture to follow. Maybe you've done it already, but probably not. So let's now look at our basic problem again. For all of linear algebra, the basic problem is like our 2-mass problem, how to solve a system of linear equations. Then you can write in simple matrix form. So on the bottom of slide 5, we have our basic linear algebra, linear set of equations. So here equation 1 is our matrix A times a vector B is equal to another vector B. We know A, we know B, we don't know X. So that's what we have to solve for. A is a matrix. If there are n, capital N equations, then A must be a square n by n matrix. For our problem, that's all you have to do. And X is an n by 1 vector. In other words, a matrix of dimension n by 1 column. So it just goes down and over. And B is another column vector, also n by 1. Okay? So that's everything we need to know. X is unknown. That's what we have to solve for. So now let's look at slide 6. So slide 6 is again how we solve for linear equations. So what we have on slide 6 is just a repeat of what we've seen before. Equation 1 is our basic equation. Equation 2 is written in more specific matrix form. Many of the textbooks will leave out the vectors, just use bold. Okay. No question, the best way to solve this system of linear equations is a technique known as Gaussian elimination. Now this is essentially the same as you would do by hand if you had to solve simultaneous equations. You would just solve for one variable in terms of all the other, substitute it back in, then you have that one variable is gone, then you solve for the next variable, substitute it back in, eliminate that variable, etc., and you go down. And then you each time eliminating another variable. So you end up with a triangular matrix because you're successfully eliminating one variable, and that's also called triangular decomposition. So the advantage to Gaussian elimination is that you never explicitly have to calculate the inverse of A, the matrix of coefficients here. Okay? So it's the most robust and the fastest way. Symbolically, though, and mathematically, when you're trying to do theory or think more abstractly, it's often nice to think of these equations in terms of you can solve for the inverse A, and surely you can do that on the computer as well. But solving for the inverse A is often slower, less robust. But we do it, and we do it symbolically all the time. And we'll ask you one of the exercises to do both. You can compare the two. So what do we have? We have equation 1, and we can rewrite equation 1 by multiplying both sides of that equation 1 by A inverse. So here's A inverse. We multiply by A inverse on both sides. A inverse times A inverse is the unit matrix, or 1. So we just get X, and we get a direct solution to our problem. x, a vector of unknowns, that's what we're trying to solve for, is just the inverse of A times B. So if you can determine the inverse, you just do a simple matrix multiplication. And we do that as well. So that's another way of solving the problem. Both methods are standard in libraries, and invite you to compare the two. But Gaussian elimination is usually considered the best. So now let's look at slide number 7. Slide number 7 talks about the eigenvalue problem. Eigen is a German word meaning own, so this is a kind of system of equations, linear equations, but each equation has its own particular version. So that's where the word eigen comes from. So the eigenvalue problem is usually written as A, the same kind of square matrix as before, X, also unknown, and the same type of column vector of unknowns as we had before, but now the right-hand side's different. We have a parameter lambda, known as the eigenvalue, and again, the variable matrices, vector of X unknowns. Okay. So this is a different equation. If you look at what we've seen before, equation 2 here, our system of linear equations is AX equals B, well, we know the right-hand side. Here, in the eigenvalue problem, the right-hand side is unknown. That's what makes it so different. Being different is not always bad, but in this case, it's hard. Okay? Because here, because we have unknowns, we still have n unknown values inside the variables, the column vector x, but now we have another unknown lambda, which we just don't know. So we have an example here of a problem in which there are more unknowns than there are equations. So a solution may not always exist. And that's true. So the exists only, that's the symbol for exist, only for some values of lambda, in some cases for no values of lambda. So you can ask the question, when do solutions of the eigenvalue problem exist? Well, they exist, and now we use inverses again, even though you don't want to use them on the computer too often. Well, they exist because you can look at this and say, aha, let's write this equation 1 by something equal to 0. So we have A times X, then we have minus lambda times the unit identity matrix times X equals 0. So if we now multiply both sides of equation 3 by the inverse of this thing in parentheses, A minus lambda I inverse, on both sides, we would get X equal to 0. So that's a solution. That's always a solution of the eigenvalue problem. If you look back here, since X appears on both sides, an eigenvector, which is what the column vector X is called, equal to 0 is always a valid solution. But it's a trivial solution. It doesn't tell us anything. So then you can ask the question, okay, when does a non-trivial solution exist? Well, it exists when you can't do what we just did, when something outlaws it. So if we say, well, maybe the inverse here doesn't exist, then we can't multiply both sides of the equation. So the condition for a non-trivial solution is that the inverse doesn't exist. And if you remember Kramer's rule, which is used to calculate inverses, Kramer's rule always involves a division by the determinant of A minus lambda I. So if we can't divide by that determinant, because that determinant is 0, then the previous steps wouldn't work. So the uniqueness of a non-trivial solution is what's known as the secular equation here, which is that the determinant of A minus lambda I is 0. So that's how the eigenvalue problem is solved on a computer, in one form or another. So what does that involve? Well, you need to have some library routine which calculates the determinant, which you can do, and then once you know the value of the determinant, you need to search on the values of lambda here, different values of lambda, to see which values produces a 0. And that's what the eigenvalue routines do. They do it in their own way. We're not going to talk more about it. Okay, so now let's look at slide 8. Take a break. Look at slide 8. We've spoken about some of the general conditions. Now let's talk about some practical aspects of matrix computing. Things you need to know in order to get the right answers on a computer. I don't mean to scare you, but I do mean to try to make you careful. Probably more scientific programming bugs occur in dealing with arrays than occur any other kind of computing. It's easy to make mistakes. You deal with many arrays. They're big, they get complicated, and you just make mistakes. You have to be careful. On computers, we use the term array, and an array is just a what is an array? Well, on a computer, you usually think of array like a matrix. It's just any dimensions, one here, two dimensions here on the screen. It's just a bunch of numbers stored with several indices. Here with 2 indices, if we wanted to have a 3-dimensional array, we could imagine having numbers stored in like a 3 dimensions. And that would be a 3-dimensional array. So when we speak of a vector, as we have here on the right, we're speaking of a 1-dimensional array. So we would define an array on a computer by giving a subscript n, and if it's only 1-dimensional, then it's called a vector. Column or row vector is independent of on the computer. They're both the same because we're just storing 1-dimensional arrays. Okay. So that's the term. What about rules of thumb? Things we should remember to not make too many mistakes. Well, the first rule is the obvious one, that computers are finite. So no matter what computer you're using, and no matter how much money you spend buying it, buying all the memory, it's still finite, and you can still slow it down, make it stop, make it fail even if you get your matrices too big. Take too long. For example, let's say we have an array here, A, 1, 2, 3, 4 different indices, okay? Each one of 100. Well, that happens to be about a gigabyte of memory. And a gigabyte's a lot of memory. You may have that much in your computer, but if you're using it to store just one vector, that leaves no room for anything else, and your computer will slow down, your system may fail. So that's not so big. Many practical problems, say you're doing the census for the United States, you want to have an entry for each person, for each state, for each ethnic group, for each year, for 100 years. You can often have a number which is much bigger than that. You have to be careful. Okay? If we have an array, let's say here a 2-dimensional array, n times n, how many steps is there in any matrix computation? Well, typically it's not unusual to have about n cubed steps. So the number of steps goes like the dimensions cubed for the square array, and that's because you have n squared elements, and the elements have to interact with each other in one way or another to do the computation. That goes like n cubed. So what that means is if you double the dimension, the size, that would lead to an 8-fold increase in time, at least for this simple 2-dimensional case. Or if you say, let's go to a little bit higher resolution, 10 times more resolution, that would mean 1,000 more steps, 1,000 more times. So it may have taken you a few seconds or a few minutes, suddenly starts taking you days of work, and you need a bigger computer or something. Okay, page faults. Always the bottom rule in dealing with matrices, particularly dealing with memory, avoid page faults. So you may say, okay, I want, I have some array here, and I want to deal with one little element. Fine. You just say, I just reference that element. Well, the computer doesn't store one element of an array at a time. It has a whole page with other elements as well. And if your element that you need is not there, the computer has to copy over this whole page into memory. It's called a page fault. It makes the computer very slow. So as we'll see, we have to avoid that. Okay, so let's look at slide 9. Slide 9 are more practical aspects dealing with memory and matrices. Well, we think of a matrix stored on the computer. We say, aha, a matrix is stored as a matrix, as a block of numbers. Okay? Well, that's good for us, but the computer stores stuff in a linear fashion. Okay? So rather than, having our matrix here with all its different elements in 1 dimension, or we can move this to 3 dimensions, we like to think of the elements extending then in 3-dimensional space. That's not how the computer stores it. In Java and C, the matrices are stored in row major order. In other words, here's a matrix A, B, C, D, E, F, different rows, different columns. They're stored linearly as a string A, B, C, D, E, F, G, H, I, etc. And what that means, of course, is if you wanted to say, I wanted to go from A down to D, the next element in the column, you have to jump from A here all the way to D, there it is, around. So that could be efficient, could be inefficient. You need to think about that. Fortran uses column major order. So the matrix A, B, C, D, E, F, G might conceptually still be in a block, but it's actually stored down columns first, and then they jump up rows, then they jump up. So if you want to go from A to the next element B, here's A, you'd have to jump a whole bunch of steps. So your algorithms need to know this. And the rule here is avoid large strides. Strides being the size of the steps you take in getting from one element to the other. You need to keep that as small as possible. One way of doing that is kind of obvious, and it's something you can program in. And you can easily get into bad programming habits in dealing with small matrices, but when you scale up to hundreds and thousands and hundreds of thousands of elements, it matters. So for example, in equation 1 here, we have a matrix with 1, 2, 3, 4, 5, 6, 7 indices. And that's a lot, and often that means it's spread out in memory, huge banks of memory, and you have to jump all around. Well, if you just break this up into here 3 matrices that will be dealt with independently, it doesn't take up any more storage, but it's a much more efficient way of getting to the elements. Okay, so that's one example. Another thing is practical aspect of memory usage that you have to concern yourself with on computers is that often in mathematics, we'll write with indices starting at 1 or 0. The computers, Java and C, start with 0 usually. Fortran used to start only with 1. Now you can start with either. Okay? But if you have an algorithm, for example, here for Legendre polynomials, this is written assuming L can be 0. And if you've coded things up so you're always starting at index 1, it'll be the wrong algorithm. So the two have to match. Another aspect, which is often confusing, but it sounds confusing, it's not really, is you have both physical and logical dimensions when you deal with matrices. So physical dimensions is the actual size that you store on the computer. Logical would be how much you're using for any one problem. So let's say here it is an example, equation 4. Let's say we have an array A, which we've declared to be 3 by 3, but we've only defined, here with a little red dashes, elements up to 2 by 2. So if we look at the array on line 4, we have A11 defined, A12 defined. This is A13 is now undefined. And then we have A21, because we're only going from 1 to 2, defined, but A23 is also undefined, and everything else. And so you see here a very unusual aspect when you're not familiar with this. If you look at the elements, they're stored linearly, automatically, because that's how computers store them, and some ones are defined and other ones are undefined, mixed in between. So if you suddenly get a garbage type number as an output when you deal with matrices, that probably means that you've run into an undefined number. You've jumped to some other element which has never been defined, which is good because it's telling you it's garbage, telling you you've made a mistake, and that's typically the kind of matrix problems you have to deal with, kind of errors. Okay. Slide 10. Slide 10 is like yellow pages in a phone book. Look at it while I take a sip of tea, please. So here we have various libraries, subroutine libraries that I've been trying to push and sell to you that you can use. You have to find them. They're usually available on the World Wide Web, and many of them are excellent. A good place to start is Netlib, and that's just a meta library of including links to various different libraries to do different things. One of the most famous libraries is LAPACK. LA describing linear algebra, and pack meaning package. So that's the standard. There is now an LAPACK++, which is obviously for C++ language, and there's a scalar LAPACK. And what scalar LAPACK does is it scales up parallel computers. So if you're using LAPACK subroutines on your laptop, your desktop, and this is typically mainly Fortran, you can go use it in C, you can run it in parallel as well. Very good. SLATEC is one, came from the national laboratories. It's more comprehensive. It's not just linear algebra. It has various mathematics, searching routines, as indicated on the bottom here, signal processing, etc. We've used it. It's been wonderful. It's also free. Some of these, like IMSL here, which is International Mathematics and Statistics, NAG, comes from the English National Libraries. These tend to be proprietary. They cost money. But often your facility you're at may have license to them, and they're just excellent libraries to use. Other ones like ESSL is the Engineering Scientific Subroutine Library. This used to be proprietary for IBM machines. Now you can get it free on the web. But it tends to be implemented only for IBM machines. But if you're on an IBM machine, you can use this as well. CERNLib is the Center European for Research Nuclear, is an excellent collection, very high-powered. If you're doing particle-type analysis, it's wonderful to get. The library we will use, and I'll give you some demonstrations of now, particularly because I'm tired of talking about words, is JAMA, which is the Java Matrix Library. It comes from the National Institute of Science. It does some wonderful things in Java, which is what we've been using. So look at these, come back to these. If you're doing some of the processes on the bottom, signal processing, eigen analysis, numerical quadrature, this is a good place to look. It's not trivial to find exactly what you need, but it's worth the investment. Okay. JAMA, 11 slide. Take a look. JAMA is free. It's the Java Matrix Library. It comes from the National Institute of Science and Technology, and it's very nice to use. It's the basic linear algebra packages. It works well, as we'll see. It's natural to use. It's not designed for experts, and it's free. There's a companion to JAMA, which is JAMPACK, and that works for complex matrices as well. JAMA only works for real matrices. One of the really interesting aspects of JAMA is that it's written in Java and takes advantage of an object-oriented language, and matrices, after all, as we've already said, are abstract objects. They contain elementary parts, and this language treats them as new entities, basic variables. So there's new matrix objects, just like the doubles and singles and floats. There's now matrices, which we can do with it. It does all the usual linear algebra routines, and it produces very nice output, which is nice when you're trying to look at what your matrix looks like. So let's look at an example. Here's our classic problem. AX equals B, linear algebra problem. And on the bottom of slide 11, you actually see how you would use this in a program in Java. And as you see, we start off with an array. Okay, so and we're just calling the variable array as a name. That's not a type. It's a double in Java. And when you put two indices here before or after the double, or the array rather, before or after the array, that indicates that this is a double indexed object and a double precision object. So this is the array. Here's row 1, row 2, row 3, put in braces. So this is standard Java for an array. Has nothing to do with matrices. But now we see here on line 2 how we've defined a new matrix object. And you'll say, aha, this is the standard way of creating objects, because we have matrix, repeated again, and the word new. So one defines it to exist, and the other actually creates it in memory. And what this is doing is it's taking this array of these 3 rows and making a new matrix called A out of that array. That's all it took. Now here we do it another way. Here we say, let's define a new matrix. So there's matrix, matrix, and new. We don't have to say new here because we're doing something else. Here we're saying matrix B is now a 3 by 1 matrix, so that's a vector, and we're just filling it with random numbers. So we're taking matrix, the dot operation here is a standard for objects, and it says just fill that up with random numbers. Pretty neat. Now let's do something. Here's our problem. So we have a matrix A, which we've defined with rows. X is the solution we want, but it's unknown, so we can't define it even if we wanted to. And B is just a bunch of random numbers. And if we, to solve the problem, we just say line 4 here. The new matrix X, our solution, we're defining it as a matrix, is A dot solve. So solve the matrix linear algebra problem with B being the right-hand side. That's it. That's all it takes. That's the solution. And the residual here is what? Well, the residual is, well, how do we test if we have a good solution? Well, we test by taking A, multiply it by X, and then subtracting B. And in computer science and linear algebra, numerical analysis, that's called the residual. Okay, it's how much the solution differs from what it has to be. So this is A times X, which we know should be B, and then we're subtracting the actual matrix B. So this answer should be very close to 0. So it's a test. Finally, on the last line, another test here is to take, okay, let's define a new matrix I test, which should be the unity matrix, the identity matrix. Take any matrix A here, it could be the same one we've defined above, dot with the parentheses finds its inverse. So that's the inverse of A, and now let's multiply it by A. So this is times. So this is A inverse times A, and test the inverse. So look at this again. There's other examples. It's as easy as that. As I said, it's very natural. So now let's look at slide 12. Now it's worth looking and pausing because slide 12 is a real program. So if you go on the web, maybe, certainly if you go out in the textbook and on the CD of the textbook, you'll find Java codes, and one of the Java codes directories will be JAMA eigen. So in JAMA eigen, you'll find this program, JAMA eigen.java. So it should be on the CD. This is what it looks like. And let's talk about the program. So this is one of the sample programs we give you. This is the eigenvalue program. So it shows you how simple it is to use this library and how you can get some sophisticated answers. And we'll do a demonstration of this in a moment. So as usual, we start off by importing classes. Here we have to import jama.star. So these are all the classes. So these are the classes of the methods and the data. So these are the methods which will do all these computations for us and also define what we mean by matrices. And this import statement, the IO, that's the standard just to give us the various classes that do input and output in Java. Fine. So here's our program, JAMA eigen. It defines the class, JAMA eigen, which has these elements in it, and all it has here is a very simple class. It's just a main method. So the usual main method. And now we're doing the same as we saw previously. We're taking an array. Here we're calling it I not being the identity here, but being the moment of inertia for some problem. And we're saying it's a two-dimensional array, row 1, row 2, row 3. So it's an array, a square array. Okay, so that's I, with which defined here. And now we're saying matrix version of I is just a new object, a matrix object, taking the array. So now we've made it. So we've converted an array to a matrix. And now we say, let's print it out. So we're telling you, here's the input matrix. And now, very nice. Here's our matrix object, matrix I. And we just operate on it with a dot operation, which is how you do, just say print. That's it. And it just prints it. Here we're putting in two arguments. We're saying 10 and 5. So we want to print out each element using 10 spaces with 5 after the decimal point. So this is much like the kind of output you get in C and Fortran, where you can really be specific about what you want the matrix to look like. Line 10 here in this beautiful greenish kind of color is the full eigenvalue decomposition. So this is the whole shebang right here. we take our matrix, matrix I, so that's over here on the right, and now we just say, do an eigenvalue decomposition on it. And let's E, it's a new matrix we defined, and here's new, which is creating it, is now a matrix which will contain all the eigenvectors and eigenvalues. Okay, so how do we do that? Well, we just did it. That's all you do. That's line 10. Then on line 11 we say, okay, let's now take our matrix E, let's get the real eigenvalues from it. We just operate with the dot operator, get real eigenvalues as expected, and that extracts all the real eigenvalues. Likewise, if we can replace real by imaginary, then we would get the imaginary eigenvalues. Okay? So even though JAMA deals only with real matrices, when you solve the eigenvalue problem, even with a real matrix, you often get complex matrices out, so this can handle it. Okay? And now here, this is just standard. We're just outputting with a tab character the real part of lambda, and then lambda here is the array in which we store the eigenvalues, and now we're just putting some values there. And likewise, if we wanted to get the eigenvectors, we define a new matrix V, get V from E, so E contains all the information output from the sub-method called. Now we just get the vectors, and we'll print that out. So let's do this for you. So let's take a little stop here. We'll stop the PowerPoint. Okay, and here, as you see, this is now a directory which I have in front of me. Yeah, and you look and you see, aha, look at this. This is the JAMA CP directory. Okay, so this is one of the directories you should have on your CD, and it has the class over here of JAMA. Those are all the class files. So that's a directory with all the class files. And these are now the .java. These are the examples. So one of the ones we'll talk about is JAMA eigen.java. I've already compiled it right before class to save you that. But now we can get some space. Now we can run that class. So if we just give the Java command, Java JAMA eigen, okay, that'll run. Aha, you see, you never trust anyone who talks about programs unless they're willing to run the program live in front of you. If it's just PowerPoint, you don't even trust the output. So this is the real thing. So this is the output, and as you see here we've said JAMA eigen. So this is the just run command that executes, and then as we asked it to do, first it prints out the line input matrix, and this is the input matrix. Very interesting. Okay, those are the same ones we put in, and notice how they're printed out columns, order 1, 2, 3, 5 decimal places after the decimal point. That's what we said it should be. 10 spaces, so that's why there's blanks between them, because we added some extra space. And these are the eigenvalues. So lambda.real, the first one we printed out, is equal to 0.166. The next one's 0.91. And the third one is 0.91. In the code, I only had one printed out because I couldn't fit it on. Here we printed out all three. And then this is the matrix which comes out, the matrix of the eigenvectors. So these are the three eigenvectors corresponding to these three eigenvalues. In the code on the CD, but not what I just showed you here, I actually show you how to separate off each column of this vector using just some of these simple calls. So here is the column of first eigenvector extracted separately, and then we test it. We test by calculating AX and seeing if it's equal to lambda x. So the left-hand side and the right-hand side are computed. This is the left-hand side, this is the right-hand side, and lo and behold, they actually agree. Okay, so let's come back. That's the output for our program. So we've done that. Okay, so we're nearly done. On the subroutines lists given for the Java and given under JAMA CP, you'll also find JAMAFit.eigen.java. JAMAFit is another JAMA subroutine I recommend you look at. It has many examples, and what it does is it fits the polynomial b0, b1x, that's just a parabola. If it's a parabola, to data. We show you how to do that. We'll talk about that shortly, how you do that. But it shows you how to do that using many of the same routines. I suggest you look at that now. But before we get on, I'm tired. You should be tired. Before you try to use this for anything significant, let's go to the lab and try using JAMA. Use it on some sample test problems. So let's do that now. So thank you for sitting in. Hope this has been fun. Bye-bye.